Well, all right, orthogonal sets. So orthogonal is a synonym for perpendicular. And we have studied in this class different sets of linearly independent vectors. But certainly if you have a set of vectors that are perpendicular to each other, those, I mean, geometrically, though that's about as linearly independent as you can get, so to speak. So a set of vectors, okay, uh, a set of vectors is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, if the dot product of the vectors are all equal to 0. So for instance, in example 1, you have 3 vectors. You have u1, u2, and u3. And if we look at the dot products of u1 with u2, u1 with u3, and u2 with u3, if we look at all of these dot products, we end up getting zeros. And they drew the vectors u1, u2, and u3 as well in figure 1 there on the left. And the vectors are orthogonal. So you have an orthogonal set, and the vectors, those 3 line segments, those vectors are mutually perpendicular. Okay, now it's sort of obvious, but if you have, by theorem 4, if you have a set of orthogonal vectors, then that set is automatically linearly independent, and hence is a basis for the subspace spanned by the space. So let me just show you another kind of nice example of this here. One moment, let me get my stylus. Okay, so let me just draw here. X1 axis, X2 axis, X3 axis. So here's the first vector I'm drawing. Here's the second vector. The first vector I'm drawing goes out to the point 1, 0, 0. The second vector goes out to the point 0, 1, 0. And the third vector goes out to the point 0, 0, 1. Okay. And these vectors, you commonly know them in this class as E1, E2, and E3. And if you look at the vectors, E1, E2, and E3, okay, those vectors are clearly orthogonal because the dot product of E1 and E2 clearly equals 0. The dot product of, so how do you get the dot product? Remember what you do. You take the components, the first components, multiply them together. Take the second components of the vectors, multiply them, and add. And then take the third components in this case, because these vectors live in R3, multiply and add, and you get 0, right? So you learned how to do a dot product, or an inner product, they call it, in section 6.1. The dot product of all pairs of these vectors is equal to 0. And notice that the vectors, I mean, the E1 vector, like if you're thinking like in a physics class, what would you call the E1 vector? You would call it a different name. You would call it vector what? It's a unit vector or linear out. Yeah, that's right. You would call it vector I. That's right, Mikhail. And the E2 vector would be called what? Vector J. And the E3 vector would be called vector K. How many have heard of vectors I, J, K? I mean, I'm sure you have, but yeah, Mikhail has, Marcella has, and you might wonder, why do they use those? Why do we take any coordinate in three-dimensional space? And like in many classes, many courses, they use the basis vectors I, J, K, or E1, E2, E3. It's because it's very easy to see that those vectors are perpendicular to each other. It's very easy to see that. You know, it's extremely easy. You can even eyeball it and see that, you know, you have an orthogonal basis. And the vectors are linear, yeah, and of course the vectors are linearly independent. So when I think of the comment here where it says if you have an orthogonal set of vectors, then the vectors have to be linearly independent. I think of the IJK vectors, okay, or E1, E2, E3 vectors. And that's a basis for R3. So I always like to think of examples to just sort of to help me feel comfortable with the concepts. Okay, are there any questions on that? All right, well, let's proceed on here. Let's proceed on. So theorem 5 is certainly an important theorem. So up to now, like for instance, let me go to the whiteboard again. Let me go to the whiteboard again and show you, you know, what we're getting at here with this. So you can have a basis for R cubed. And let's say that basis is vectors v1, v2, and v3. Let's say that's your basis for R cubed. And you might say, is a vector x in R cubed a linear combination of v1, v2, and v3, okay? Okay, so is the vector x in R cubed? If you have a vector x and it's in R cubed, is it a linear combination of v1, v2, and v3? Well, we know the answer is yes to that. That's right, Mikhail. By definition of a basis. If this set of vectors, v1, v2, and v3, since it is a basis for R cubed, for three-dimensional space, any vector in R cubed can be written as a linear combination of the basis vectors. And so there is a C1 and a C2 and a C3 such that C1 times V1 plus C2 times V2 plus C3 times V3 equals the vector X, right? And maybe I'll tell you what, just so I want to relate this to theorem 5, maybe instead of vector X, I'll say we have a vector Y, okay? It doesn't matter, but let's say vector Y. Okay, and so what we'd have to do is solve this vector equation for C1, C2, and C3. Okay, and that of course leads to the augmented matrix. This here. Right, and you solve. But the point is you have to solve a system of equations in order to find what the linear combination is. And that's how you've had to do things up to now. But now in section 6.2, we're saying, well, we have a basis for a subspace, but this basis is an orthogonal basis. And the question is, will that make it easier to find the linear combination? For instance, C1, C2, and C3. And the answer is yes. The answer is yes. Absolutely. So let's go to the theorem here, theorem 5. So here it is. In this theorem, we suppose we have a orthogonal basis for a subspace, and you have a vector y in the subspace, and we want to be able to write the vector y. We want to be able to write the vector y here as a linear combination of the basis vectors. Well, it turns out that the coefficients, for the linear combination, can be found simply using this formula. Just take the dot product of the vector y with whatever. So if you want to find the coefficients, or let's call it coefficient, or the linear combination constant C sub j, just take the dot product of the vector y with the jth vector u and divide it by the dot product of that jth vector u with itself. So see, with an orthogonal basis, that's a very special basis because you have a formula. You have a formula here that allows you to find those weights in the linear combination. Now, the proof of this is not hard. It's not hard. It's below here. And what I'll do, let me just sort of talk about it briefly. So let's say that you wanted to find C1, okay? Let's say you wanted to find C1. They're taking the dot product of y with u1. Well, I'll tell you what. Let me this proof. Let me go to the whiteboard and just do kind of a nice example so you can see it here. So here's the vector y, and let's say that you have three basis vectors, u1, u2, and u3. Okay, and you're choosing. You're choosing to take the dot product. Hold on, this is not what I want. No. No. This is not what I want. Let me do it again. Let me be more clear. So let's say the vector y is a linear combination of your basis vectors. Okay, but you're curious what, for instance, C1 is. Well, what you can do is you can take the dot product of y with the vector u1. Okay, I mean, you can take the dot product y with the vector u1. And then by properties of dot products or inner products, you can write this dot product this way. Please let me know if you have any questions. So far, so good. Are we good so far? Okay, wonderful, wonderful. Okay. Now, we're assuming that, again, U1, U2, and U3, we're assuming it's an orthogonal basis. Okay, for the subspace that vector y lives in. This means what's the dot product of U2 with U1? What would that equal? That's right, Mikhail, 0. And the dot product with U3 with U1, that inner product would equal also 0. Yeah, because you have an orthogonal basis. Those basis vectors are perpendicular to each other, so their corresponding inner products would equal 0. So that means all that's left now is y dot u1, Mikhail's seeing this now, equals c1 times u1 dot u1. Okay, well, and of course u1 dotted with itself wouldn't equal 0. So this means then that you can solve this equation for C1. And so C1 will equal y, the dot product of y with U1 over the dot product or inner product of U1 with itself. That's how you get C1. Now, if you want to define C2, well, you would take the dot product of y with U2, and you do some work, and you would end up showing that C2 is equal to the dot product of y with U2 over U2 dotted with itself. Okay, so that's how this works. And if it's in the recording, but there you go. See? All right. So again, with beauty in math, there's usually benefit. That's a saying. I just kind of made that up, but I'm gonna beauty equals benefit. That's what I've noticed in math. And an orthogonal basis is usually, in a sense, more beautiful than just a regular non-orthogonal basis. And here's one of the things. Here's one of the properties. All right, are there any questions before we proceed on here? Well, Jacob, you know, uh, if you strive to do your best in life, usually beauty will find you. Okay, usually beauty will find you. All right, good question, good question. Because it's a beautiful thing, right? To strive hard in your life, do well, try to do your best, try to be honest. It's a beautiful thing, and people like that. That people generally like that. All right, good philosophy there. All right, now example two. Okay, here's thank you, Jacob. Appreciate it. Um, so here's a set S, and that's a set from example one, and they want you to find express the vector y as a linear combination of those vectors. Okay, so the example one is have to go up a little bit here. There's example one, those three basis vectors. And so vector y in three-dimensional space is some linear combination of those three basis vectors. And how would you find it? Very simple. Very simple. You just utilize the formulas in theorem 5. You utilize the formula in theorem 5 to find the, let me see here, I want that to go up a little bit. Yeah, there's the CJs, okay, the weights from your linear combination. So now you just apply that, and you see how in this vector, well, vector y, you see they're not solving a system of equations to get the to write y as a linear combination of the basis vectors. They're utilizing that formula in theorem 5. That's what they're doing. Now see, and notice below, it says, notice how easy, hold on. Notice how easy it is to compute the weights needed to build y from an orthogonal basis. If the basis were not orthogonal, it would be necessary to solve a system of linear equations. Okay. 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 So let's proceed on here. Let's proceed on in the book. Next, we have to talk about orthogonal projections. Okay. Now, how many maybe have taken Math 280, have taken multivariable calculus, and have seen projections in Math 280? You would have seen a little bit of that. Okay, Marcella recalls that, and David recalls that. Yes, and actually, in multivariable calculus, you learn that right after you learn the dot product. All right. Well, yeah. Okay, Mikhail, sure. And Mikhail says this reminds him of physics. Excellent. The formulas you learned, the projection formulas you learned in like if you take Math 280, they're used for 2- and 3-dimensional examples. But a projection in linear algebra can be done for an n-dimensional example. So the setup is what you see here in figure 2. Okay, in figure 2, what you have, this is from section 6.2 in the textbook, naturally. Figure 2, you have a subspace W. subspace W, and that's the green subspace there. And then you have this vector Y that is not in the subspace, okay? The vector Y is not in the subspace, clearly, because look at the vector Y, it's outside the subspace. Now, if you project Y down into the subspace W, you get what's called the projection of the vector Y onto the subspace W. So in figure 2, the Y hat there's a Y vector. So you see that dot in the, that has the Y hat below it. It's a Y vector bold. So it's a vector with a hat above it. That's a way of denoting the projection of the vector Y onto the subspace W. And the vector Z, which is the difference between the vector Y and the vector Y hat, okay, is simply, it's the same vector as that dashed, that vector, that Z vector, which equals Y minus Y hat, that's the same vector as the dashed line segment that you see, because vectors are defined by direction and magnitude. And what we want to do is we want to determine, well, so the vector Y, you see here, now, hold on. So they're saying the vector Y is equal to the sum of the vectors Y hat plus the vector Z. That absolutely makes sense. Tip to tail, you add vectors tip to tail. So that makes sense. And they notice that the vector Y hat is equal to some multiple of the vector U. So if you, now hold on here. So, in this problem, what we're doing is we're decomposing a vector Y as the sum of two vectors. One vector is the multiple of a vector U, and another vector will be orthogonal to U. And so the vector Y is equal to Y hat, which is a multiple of the vector of, say, a vector U, okay, that is in the subspace W. All right, and we want to find, really what we want to do is we want to find now what that alpha is. Okay, because if we're going to find the projection vector, it has to be some multiple of the vector U. And so what they do is they do something similar to what you saw with the proof of theorem 5. They're going to take the dot product of the vector U with the vector Y minus alpha U. And because those two vectors, Y minus alpha U is Y minus Y hat, that is orthogonal to the vector U in the subspace W. And using the property of dot products or inner products, it turns out that the vector 0 is going to equal Y dot U minus alpha times U dot U. Well, if you solve that, you're going to see then that alpha is equal to the dot product of Y with U over U dot U. And Y hat is going to be then that coefficient alpha times the vector U, because Y hat is a multiple of U. The vector Y hat, again, is called the orthogonal projection of Y onto the vector U. Okay. And so now you have a formula. Okay, to find this projection. And you'll see that if you ever take multivariable calculus, or if you've taken it, or even taking it now, that formula y hat is the same formula as what you'll see in multivariable calculus. It's the same formula. Absolutely, absolutely it is. So what you might see, yeah, so like, okay, Mikhail says same formula in physics. Right, so let's do an example. Let's do an example just to make sure we have our heads strong on this. We want to be strong on this. So let's do an example here. Mikhail says it's used for some force calculations. Okay, like if you want to decompose the force into different orthogonal components. Yeah, okay, Mikhail, makes perfect sense. Absolutely. All right, well let's do a quick example here. Let you copy this example down, and I'm going to make a call out again to Jonathan. Jonathan, are you here? Can you hear me? Give me a thumbs up. All right, go ahead and copy the example down, and then we'll discuss this example. Okay, so let's see what we have here. So we have a vector y, which is equal to 7, 6, and a vector u, which equals 4, 2. Okay. And what we want to do is we want to find the orthogonal projection of the vector y onto the vector u. And then what we want to do, okay, what we want to do is we want to write the vector y as the sum of two orthogonal vectors. One in the span of the vector u, and one that's orthogonal to u. Okay, so pictorially, let's go to the next page here, and there's a picture here on top. Okay, there's a picture here on top, and actually this picture, I mean, this goes with example 3 in the textbook, but this figure 3. So hold on here, one moment. Hold on. One moment. Right. So this vector 7, 6 is the vector y. And that's this vector right here. Okay. That has coordinates 7, 6. And the vector u right here has, maybe I'll put that in red, that has coordinates 4, 2. Now, what we're trying to do here, let's try to clean this up a little bit. Let's make this look good. Yeah, that has coordinates 4 and 2. So you see when you have the span of the vector u, that's just all multiples of the vector u. And so that's going to generate what's the subspace going to look like? Well, I'll show you here. Hold on. It's going to look like this line, right? That's what the span of the vector u is. It's all multiples of that vector, which is going to generate a line in two-dimensional space. And the vector y hat, okay, is right here. So notice you have a right angle here. If you project the vector y onto that space L, which is the span of the vector u, okay, the projection vector is going to be right here. And we need to find what that projection vector is. Okay? That's the scenario that we're talking about. Now, we learned, well, are there any questions on that so far? All right. Well, so the projection of the vector u onto that subspace L is simply given by, it's a multiple of the vector u, and the multiple is equal to the dot product of y with u over u dot u. And when you compute that all out, you're going to get 8, 4. Okay, a vector with coordinates or components 8 and 4. And if you look on the picture, yeah, that's pretty much looks right. Okay, the vector y definitely looks like it has component or coordinates 8, 4. Okay, so this is how you do it. And linear algebra is actually, for components, it's a nice way to understand. I mean, for projections, it's a very nice on how you know, how it treats it. You know, projections are going to be so important in this class. Now, Mikhail's already seen them in physics when you have to decompose a force into two orthogonal vectors. And you're going to see a lot of it here, a lot of applications. Yeah, very nice. Okay, and you know what we want to do is we want to go a little further here and try to figure out this vector there, right? Because the vector y is the sum. I mean, if I were to try to maybe, let me see, maybe I can use this color here. Whoops, hold on, I got on my little thing here. All right, so the pink vector the pink vector y hat, and that orange vector, which is the orange vector, is the same vector as is y minus y hat here. I mean, well, that is what the orange vector is, y minus y hat. Well, if you look at that y minus y hat there, hold on, I don't want everything, it's switching up the colors on me. Hold on, don't do that, Hold on, let's start. I want that vector to stay pink. Yeah, so you see the two orange vectors, the y minus y hat vector in the right triangle there, that vector can be drawn from the origin. So if you look at this vector here, okay, what do the components of that vector appear to be? What do the components appear to be on that vector? Yeah, -1, 2. And sure enough, that's right. Sure enough, if we look on the next page here, y minus y hat is -1, 2. And so the vector 7, 6, that vector y, can be decomposed into the projection vector y hat and the vector y minus y hat. And again, I put the picture below. So, you know, I thought a nice little simple example would help you get comfortable with these ideas. And they mention in the book, just before example 5, about decomposing a force into component forces. And Mikhail's already experienced that in his class, his physics class. Now this was an example where you had one basis vector u, and the subspace was a line which was created by taking multiples, any multiple of the vector u. What if your space were in what if your basis were in two-dimensional space? So let me just hold on one moment here. Well, actually, this is a little bit separate. What I want to talk about. Let me go. Is everybody cool on this before I go back to the book? All right, let me go back to the book here. All right, Cameron's good. Marcella's good. Excellent. Mikhail's good. Wonderful. Are there any questions? Jacob's good. Very good. Bellen's good. Excellent. Okay, wonderful. And all right. Well, let's see here. Let's go back to the book. One moment here. Okay. Okay. Yeah. Oh, okay, Mikhail. Very good. Very good. Excellent. Excellent. Yeah. Let me see here. Yeah, theorem 5. There's that theorem 5. Okay. And again, you notice that in theorem 5, the weights, the C's, those weights are just equivalent to projection coefficients. Okay, so in other words, you see how like the weights are y dot uj over uj dot uj? Okay, that is the, I want to say it the right way. Hold on. I want to say it the right way. One moment. Yeah, that is just the multiple or the multiplier for I'm not saying this the way I want to say it. Okay, let me go to the whiteboard. Let me go to the whiteboard here. Okay, so all right, we learned that y hat, if it's the projection of the vector y onto a line, okay, line L, which is equal to the span of some vector u, that projection is equal to y dot u over u dot u times the vector u. Okay. Now, theorem 5, if we just take a vector y, now I'm kind of separating things here. Take a vector y, And let's suppose that y is in R squared. We're just suppose. If y is in R squared and the basis for R squared consists of orthogonal vectors u1, u2. So we're assuming we have an orthogonal basis. Then the vector y is going to equal, let me just get it a little bit higher here. The vector y, based on theorem 5, is going to equal the dot product of y with u1 over u1 dotted with itself times the vector u1 plus the dot product of y with the vector u2 over u2 dotted with itself. Hold on. Times u2. So if you look at this here, okay, and you look at this here, what really is this first part of the vector y? It's going to be a what? What is this circled in red? It's a type of, begins with a P. That's right. It's a type of projection. It's a type of projection. Okay. It's a projection onto U1. I don't like things cluttered. It's a projection onto U1. And the second part is going to be a projection onto what vector? That's going to be a projection onto there's only one vector left. Projection onto U2. Right. Good, Cameron. Good, Mikhail. Okay. So the way you can think of this is they have a nice picture in figure 4 from section 7.2. Okay. A nice way you can think of this is, whoops, hold on. I don't want to do that. No. Let me go to theorem 4 here. Or let me go to, hold on. Should have just boom, 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 boom. Yeah. This is what I want. Hold on. Just get it. Hold on, everybody. Yeah, this is what I want. So, you see that? See this figure 4 where you have this vector y, and the vector y is really the sum of two projection vectors. One's the projection vector onto the vector u1, and the other's the projection vector onto the vector u2. And u1 and u2 are orthogonal. See how that works? Okay, I think it's kind of a nice geometric, it gives you a geometric feel for theorem 5. But theorem 5, any vector y can be written as the sum of its projection vectors onto the different basis vectors, assuming the basis vectors are orthogonal. That's really what theorem 5 says. Okay, any questions on that? All right, very good, very good. Let me just do one more thing with you here. I want to just get a little bit further through this section. So, you know, you can decompose a force into component forces. This is what Mikhail experienced in his physics class. And, you know, another thing that we should mention, we talked about orthogonal sets, but we can also talk about orthonormal sets. Okay, so you have an orthogonal set of vectors is a set of vectors that are perpendicular, but you have an orthonormal set if those vectors, those orthogonal vectors, are also unit vectors. Okay, then you have an orthonormal set and you have an orthonormal basis. So what they're doing in example 5 is they're saying show that these three vectors are an orthonormal basis. So the orthonormal basis that, of course, that you're used to is the IJK basis, or the E1, E2, E3 basis, right? But here, I mean, it's really not hard. It's really not hard what they're doing. They just have three vectors, V1, V2, V3. And incidentally, you can see the picture here in figure 6 on the left. They just show that those vectors are orthogonal and all of them have length 1. All of those vectors have length 1. So you see that in figure 6, there's V1, V2, V3. It's like taking the x1, x2, x3 basis vectors and tilting them. It's like tilting them, you see? So see, that's another orthonormal basis, and it might be more suitable if you're dealing with a certain kind of crystal lattice or something like that. All right. Further, theorem 6 says that, hold on here, I don't have that. If you have an m by n matrix U, it has orthonormal columns if and only if you take the transpose of U with U, that's going to give you the identity. So U transpose would be an n by m matrix, and U is an m by n matrix. So the identity is n by n. And if you have a matrix U whose column vectors are orthonormal to each other, then U transpose U would have to equal the identity. And they show that below in the proof. It's a fairly simple proof. They show it here. Okay, very simple proof. And then they talk a little bit more. They talk a little bit more here in theorem 7 about if you have a matrix U and you multiply it by a vector X, part A there says that the length, so I like doing this because it's reviewing concepts. You learned about length in section 6.1. The length or magnitude of the vector U times X is simply equal to the vector X. And if you take the dot product of Ux with Uy, that's the dot product of X times Y. So the dot product of X and Y. So these are just, theorems that are supportive of the main concepts. And, of course, in the conceptual questions, true, false questions, these kind of ideas are going to be reviewed, so to speak. Okay, I think I want to stop there and give you a little break. Are there any questions before we're done with section 6.2? Are there any questions at all? Cameron's good. Wonderful. Wonderful. Okay, I will stop the recording. Very good.